Let me start sharing. So again, just to remind you that we are doing synchrotron radiation, and we sort of talked about like a less mathematical but qualitative picture in which we invoke this effect that if you have relativistic particles, uh, there is a forward beaming along the direction of the velocity of most of the radiation. And then we looked at this picture in which we consider this part of the orbit and an observer, and we see that this observer sees intense light only for a short duration, only for a small part of the full circular orbit. Right. And so this is sort of the geometry that you should always keep in mind. So you have this this helical motion of electrons in magnetic fields, and so the observer, when the observer is in the same at the same angle as the pitch angle, then you get the maximum radiation, right? That's sort of like viewing it through this direction of the velocity, right? This orientation of this observer corresponds to seeing in this direction where there is full beaming that you get. And if gamma is very high, you don't see much radiations away from this sight line. Okay, so sight line corresponding to the pitch angle sees maximum radiation. So if you have a fixed pitch angle of particles, you only see radiation peaked in that direction. But in general, we have like a distribution of pitch angles, so you will see radiation in other directions as well. What else? Right, so this is the temporal signature that, if you have this, if you only see this part of the orbit, you see this intense pulse of very short duration separated by the cyclotron orbit frequency, omega b, 2 pi by omega b. And this, because of this very short duration, and this short duration is given by this here. Right, and there is this 1/2 gamma square factor picked up because of this light chasing light effect, in which if the object is moving close to the speed of light, the duration observed by the observer can be very short compared to the duration of the event in the frame of the particle itself. So this T2 minus T1, which was calculated in the lab frame, was just this time duration in which the radiation beam is pointed towards the observer. But because we are interested in the time and the electric field measured by the observer, we have to divide this by this 1/2 gamma square factor. And so it gives this relationship between the duration of these short pulses of electric fields and the cyclotron, magnetic cyclotron frequency. Okay, so then I actually, so this frequency gamma cube omega b sine alpha is very, very critical, right? So then I argued that this electric field measured by the observer is only a function of gamma theta, right? Because the beam is of size 1 by gamma. So the idea is that the electric field measured for different gammas for relativistic particles can be scaled to one another as long as you keep gamma theta fixed. So if you have a fast, very fast, much faster or higher gamma, the beaming is much narrower. But the dependence on theta actually is given, is more generically written as dependence on gamma theta. So it's a self-similar dependence on angle where gamma is absorbed in theta itself. Okay. So since electric field is a function of gamma theta, and there is a 1-to-1 mapping between this angle theta and the time. So, if this is the part of the orbit this is angle theta equal to 0. So at t equal to 0 corresponds to theta equal to 0. And this is sort of the mapping between theta and t, right? So theta by t is equal to this. And we said that gamma theta is what electric field depends on. And gamma theta is nothing but omega cube, gamma cube omega b times t, which is omega c times t. So the time dependence of electric field measured by the observer comes in the form omega c times t, right? And the angle dependence comes in the form gamma theta, right? So this particular form of angular and temporal dependence gives you a very powerful result, which was sort of motivated here, that right. So this is the spectrum, just the Fourier transform, the Fourier power, angular power, and then you divide by this time period to get power, energy per unit time per unit frequency, power per unit frequency. You have to divide by this 2 pi by omega b, and the end result is that you get something like this. The power or energy per unit time per unit frequency is dependent on omega only through omega by omega c, where omega c is gamma cube omega b, or omega c is proportional to gamma squared b. Okay, so and in the next part we sort of consider this power law distribution. So that was yes. Yes.
Sir, sir, you said E omega will have will have peaks at like integral value of omega b.
Right.
But how isn't it a continuum? It should be a like I mean, it is actually.
So these peaks are so closely spaced that you can actually think of it as a continuum. Right. So gamma cube or gamma squared gamma cube omega b is like let's say gamma is 100, right? So gamma cube is 10 to the 6. So you're looking at a frequency which is of order 10 to the 6 times the cyclotron frequency. And if at that frequency peaks are separated by omega b, right? It's like you're looking at 10 to the 6 and things are separated by 1, 1, 1. So it's almost like a continuum. You see what I mean?
Yeah, and also, sir, you drew the electric field curve. Like I could not understand that also. I mean, can you just explain if like the gamma theta dependence on E? Like there is a curve in that last slide.
Yes.
Could
this one? This one, right?
Yes.
Right. So, I mean, I have not drawn it I've not drawn it quantitatively, but I know that my radiation gets cut off at an angle theta, which is of order 1 by gamma. Right?
Okay.
We just know from aberration formula. So what I'm saying is not just that, not just the width of this envelope, but even the form of this electric field as a function of theta actually depends on gamma theta, not on theta only. Right? So the theta dependence can be more specifically written as dependence on gamma theta.
Okay.
Right? So that's what I'm saying. This is sort of motivating things. Okay. So this is just from aberration, and this I'm just saying that since the width of this thing depends on only gamma theta, the whole function itself, is likely to depend on gamma theta. Okay. So after sort of that one particle treatment, we dealt with the population, power law population of electrons, and asked the question, how is the power due to this power law distribution of electrons vary as a function of frequency? Okay, and what we did was we actually combined this power formula, sort of motivated in the previous slide, and we just added that power over all the electrons which have a distribution in energies, which is given here. Okay, all I did was this integral, and since my power is a function of omega by omega c, I make a change of variables to omega by omega c, right? So x equals omega by omega c. So there is a one-to-one dependence. So this is an integral over gamma. So you're summing over all these electrons, and you know how much energy or how much power at a given frequency do these set of electrons produce. Okay, all I have to do is just sum up all these electrons, and there is a one-to-one relationship between gamma and this x. Okay, and I do this integral, and the nice thing that I get in the end is this total power, and this can actually be due to even a single this is independent. This depends on alpha, but this scaling with b and omega is independent of this pitch angle alpha. So whatever the pitch angle is, the frequency and magnetic field dependence is this. This k will depend on pitch angle, of course. And this formula has practical utility for astronomy, for radio astronomy in particular. And what is the practical utility? Because you see a lot of sources with this frequency which is given frequency dependence of power of radio emission, which depends on the power of frequency. For example, here. So this is a real observation of a radio quasar, right? So forget about this. This is thermal radiation and lines and so on. But this radio part at low frequencies is a power law, and very likely this comes from synchrotron emission due to relativistic electrons in some jet. Okay, so from this power as a function of frequency, you can read off the spectral index. It's just the slope. Right? Once you measure the slope of this frequency dependence of power, you basically, so this S is the slope, right? S of the slope of this is this spectral index. Once you know the spectral index, you get how the electrons are distributed in gamma. So basically, from this observation, you can actually see or get a sense of how the electron number varies as a function of electron energy for these relativistic electrons, which is very powerful, right? Because this is like an observable, and this is a physical quantity. So now you can ask pointed questions like, oh, if your observed P is, for example, like a typical value of P that you get for strong radio sources is like a P of 2.3. So now you can actually ask the question, what are the physical mechanisms that can give rise to a power law distribution of electrons which have P of 2.3, right? So this actually directly gives you a constraint on the theory of particle acceleration. Okay, so this is very useful. This formula has a lot of utility. That's why this is.
Sir,
Yes.
my question comes from this photo, like the radio quasar photo. So we see that there is a black body curve, and we see that there is a curve for this emission. But
Yes.
the temperature of these two must be different, because like black
Yes.
body, nothing can emit
Yeah.
at more than black body.
Yeah, absolutely. So there are components. So if you consider an accretion disk and so on, right? So let me actually draw. For example, so quasars are nothing but supermassive black holes, accreting supermassive black holes. Why am I not able to write? Share. No, this is not good. Just give me a second. Okay. No. Let me try to get my pen to write. Hmm. Hmm. Okay, this is okay. Dang, I'm not able to write with my pen. No, this is not good. No, I don't want to use the mouse. Okay, anyway, let me actually at least answer your question. Let me see if I can do something. Hmm. Okay, your question was how can a source give you how can a source give you black body emission and radio emission both, right? So the accretion disks are actually complicated objects. No. So let's see. So you have like a black hole, you have an accretion disk around it, and in rare cases actually this accretion is a multicolor black body, multicolor disk, and this part of the spectrum, this is new to the 4/3, right? There was a homework question in homework set 1 that gives this new to the 1/3 spectrum, right? But in addition to this, you also have these jets and bubbles associated with black holes, and these jets emit radio. So they are physically distinct sort of emission mechanisms. So this is like thermal emission, and this is non-thermal emission due to relativistic electrons. Okay. So this radiation comes from this component.
The powered part comes from the jets, while
Yes,
the
this is where you have relativistic electrons and magnetic fields, and these give rise to this part, the radio part, synchrotron part, and the black body comes from this part. And not only this, there are like more complicated components. So sometimes people have invoke corona and whatnot. So these are actually quite complicated objects. Yeah. So one has to, it's not a simple single emission mechanism. So multiple emission mechanisms operate. What has happened to my pad? Okay. Okay, just a sec. Okay, let's see if it. Okay, now it is working. Oh, I'm relieved. I just had to press that button. Okay, right. So this is right. So these are all different kinds of objects. This is a radio quasar, which has these radio jets. This is a pulsar wind nebula. So you have like oops, again. Damn. Again, it has stopped working. Okay. Configuration saved. Okay, now perhaps. No. Okay, so let me actually let me see what I can do. Um, hmm. So let me actually try to open Whiteboard or some other app and see if this works there. Okay, let's see. Let's see if my pencil works here. Oh, it works. So, let me do one thing. What I'll do is I will leave and rejoin. Is that okay? Because I think it's a problem with this app, with this Teams app rather than anything else. Or I can actually just use Whiteboard for today, and I'll put that on Teams. So okay, at least it's working. So I will actually just use Whiteboard. Okay. So let me at least show what I was doing. Yes. So let me at least show what I was showing. Yeah, sorry about that. I didn't anticipate this. Sometimes these things don't work. Okay, so we were looking at this. Oh, no, yeah. So we were looking at these astrophysical examples. Okay, so like in this case, this is a pulsar wind nebula, and the pulsar wind nebula has pulsar wind. So you have a like a magnetized neutron star, which is called a pulsar, and it has this dipole magnetic field, and it has a rotation it has a rotation axis which is different from the axis of this dipole. So the magnetization is along this direction and the rotation is along this direction. So these are called pulsars, and these pulsars are pretty energetic. They launch winds, and these winds from these pulsars create a shock, and at that shock there are a lot of particles accelerated, and it emits this radiation that's shown here. Okay, so this has so again you can actually see in the radio, which is at low frequency here, it has a positive power law, but in X-rays it has a power law which looks like this. So in fact, this is a case where synchrotron emission happens in X-rays. So magnetic fields are very strong and the particles have very large gamma. So let's actually try to see, right, because your nu, right, nu of the radiation is roughly given by gamma squared, or gamma squared nu cyclotron, or gamma cube nu b. So so basically what I'm saying is that B is strong, so new cyclotron is large because it's EB by MC, and also gamma is large. If you have that case, then you can have synchrotron emission even at higher frequency rather than at radio. And the radio is self-absorbed, so this is optically thick, self-absorbed, or optically thick. Okay, so yeah, and these are different radio galaxies, which are also nothing but large-scale radio jets, are called radio galaxies. So, for example, in this case, the slope is given by minus 0.5. So you can actually calculate from this relation, you can actually calculate the power law index of the electrons from here, and you get P equals 2. That's that's like a dn d gamma going like p to the gamma to the minus 2, which is very shallow spectrum. So shallow spectrum means that you have many more relativistic particles. A steep spectrum, steeper and steeper spectrum will have less and less very relativistic particles. So shallow spectrum means hard spectrum. There are a lot of fast electrons. Okay, so this is about this portion. Any questions on this? This is very important. Like in the end, a lot of you will actually be applying the synchrotron ideas to interpret these observations. You will not need these derivations, but it's always useful to know. But this is some idea that's applied quite frequently. So is there any question on this? Okay, good. So then we can actually go to the material for the next class, which is okay. No, today is 16th. No. So I guess I will have to use the whiteboard, which I will do. Okay, here it is. So I will use the whiteboard because my pen is working on this, but I will okay, so what are we going to do today? So now we are actually doing the quantitative aspects of synchrotron radiation. So till now I sort of talked about qualitative aspects, like the fact that the power goes like gamma square UB sigma TC. The fact that the frequency, the observed frequency, cuts off at gamma cube omega B. The fact that there is a one-to-one relationship between, the power received is a function of omega by omega C, where omega C is this gamma cube omega B. So these things were sort of motivated qualitatively. Now we will actually do a little bit more quantitative treatment. So, so let's see. So if you recall, when we were dealing with this electric field and power due to accelerated charges, we had this formula. Let me actually write that down. So D, how do you make this thicker? No, not this. I want a thicker pen. Ooh. Does anyone know how to make this, how to change the properties of this? Okay, now this is just pan and zoom. No. Okay, I hate it. Okay, anyway, let me use the thin pen, it doesn't matter. Okay, so let's see. So we had this formula dw by d omega for the energy distribution as a function of frequency and solid angle, right? You recall we had E as a function of time and as a function of the direction in which you're looking at, and you take a Fourier transform and get this, and this was actually given by C by 4 pi squared. You have R E T times e to the I omega t dt, and you just take the absolute value squared. This is nothing but right, r is this distance of this object, right? So so you have like a charge distribution, and you have an observer far away, and you are sort of calculating the this was r, and you had to calculate this retarded time, and you had this r t prime and so on, right? So this is actually electric field actually calculated at the retarded time, and this you had a formula like this, and by making a transformation from t to t prime, the retarded time, we got an expression which was like let me just write it down. And you recall retarded time is equal to t minus r t prime by c, and r t prime is just this distance, so c times r t prime. This is the light, sorry, c r divided by c. Is the time taken for light to travel from this position to the observer. So r minus r naught t prime. So this is the distance between the right. So the in the time that the radiation goes from here to here, the particle travels. So this retarded time, I mean, this is going all the way back to the retarded potentials, linear featured potentials, and so let's see, c t minus t prime is the distance that it travels. So this is equal to r t prime. Okay, and so anyway, in the end, I mean, I don't have my notes here, so I don't want to spend a lot of time on this, but that we had done this, we had converted this integral to something which was given in terms of the retarded time quantity, in terms of r prime. So this is an expression in terms of omega and t, we converted into something which looked like in terms of t prime. So which was q squared omega squared by 4 pi squared c. So let me just write down this expression, n hat cross. So n hat this is this direction. And since the source is compact and the observer is too far away, n hat can be treated as a constant. So n hat cross beta e to the I omega t prime minus n hat dot r naught t prime. So this is r naught t prime is the trajectory of a single electron, for example, by c. Right, so dt prime. Right, so if you recall, we did, we went from this expression for the radiation field for electric field, which has this 1 by kappa cube, if you recall, has this 1 by kappa cube n hat cross n hat minus beta cross beta dot, right? There is this expression which is evaluated at the retarded time, of course, and then you have 1 by r, right? So this was your electric field in the radiation zone. So I mean, we start from here, and then we also had a homework problem. We had this, so we go from there to here, where we apply, what do you call it? Integration by parts, and we had to show that this beta dot n hat cross n hat minus b, this expression can be sort of, under certain approximations, can be reduced to something like this. Okay. Do some of you recall this? There was a homework problem where I had asked you to show this intermediate step where we do change of variables. Does someone remember that, the homework problem? I guess not. So let me open that homework problem. This one. Oh, problem number 8, can you see it? Hello?
Yes, sir.
Okay, good. There are people there still. So this this problem number 8, we had to, in deriving this equation, we had to use this formula for doing the integration by parts. And so we change, oops, I hate it. Becomes so big and so small. Okay, so anyway, the final expression is this. And if you recall, this t prime, just a second, the time at which you want to evaluate the trajectory of the particle is equal to t minus r t prime by c. This is the definition of the retarded time. where was the particle a light travel time ago. Right, and so we do a change of variable. So this RT prime is the coordinate of the I mean, is this distance connecting the particle at a retarded time to the observer. So so C T minus T prime equal to R T prime. Anyway, this we have already done in great detail previously. I'm sorry about this mess because this is not a good platform. Okay, so anyway, so now let's apply this this formula. Right, so we have to evaluate this for synchrotron radiation. How do we do that? Let's consider this geometry. So we have let me actually show an axis. So this is X, Y, and Z. And let me show the, so, you know, this is the particle trajectory. So this is like a, you know, so the particle is moving on a curved path, and it has a radius of curvature. It has a radius of curvature, which is, you know, which is given by A. Okay, so instantaneously any sort of curved path can be approximated by a circle close, you know, for a short distance. So that's the radius of curvature A. And we are considering the viewing angle n hat, right? This is n hat, which is in the xz plane, and it makes angle theta. Okay, so it makes angle theta with the x-axis. It's in the xz plane. Okay, so and this, so at t equal to 0, the particle is at origin and it's sort of, you know, moving in time, and this is at some time t prime. So this angle theta here is v t prime. So see, this integral is to be done, has to be done in the particle frame at t prime. So we are in the, you know, we are in the, so, you know, we are forgetting about the observer when you're doing this integral in a sense. So Vt prime is this distance of the arc. So Vt prime by A is this angle. This angle. Okay, and for this short trajectory, this is like a circle. So so here, you know, this is the tangent. This is along the x-axis. This again, of course, is the angle Vt prime by A. Right. So we need to calculate this integrand. You know, we have to calculate these things in the integrand. So the main, so a few things to note here is that this is without loss of generality. So we can actually, so if this is the direction of acceleration, which we call epsilon perp hat. So this is the direction of acceleration. So we are using our origin of time when the particle is at the origin and the direction of acceleration is y hat. This n hat can, without loss of generality, can be taken in the xz plane. That is, you are watching the particle in the plane perpendicular to the direction of acceleration. So if you recall our trajectory of these helical trajectories of these synchrotron emitting particles, right? So basically, if you have some observer looking at some, any direction, say n hat, right? This is not the same as the angle, the pitch angle, which is this alpha. This can be any direction, right? This n hat. So for a given n hat, some point on the trajectory will be such that n hat is perpendicular to the direction of acceleration. So this is the direction of acceleration. So for example, if n hat is in this direction, so perhaps this is n hat. So the particle at this location will be and let's say this is alpha. So this is not perfectly aligned. So this angle is theta, which is marked here, theta. But n hat is perpendicular to the direction of acceleration at that instant. Okay. So my claim is that without loss of generality, if you're given an n hat, you can always consider, the radiation will be dominated by particles which are at a particular phase in their rotation, where n hat is in the plane perpendicular to the direction of acceleration. Okay, so this is actually without loss of generality, that n hat, the viewing angle, is perpendicular to the direction of acceleration, right? But your theta is not zero. Theta 0 would correspond to viewing angle along the direction of velocity. So velocity, this orbit at that instant is in the xy plane. Okay, so this xy plane is actually oriented at an angle of alpha. So this is sort of the plane of this trajectory, right? So this z is not equal to the magnetic field direction. So the geometry is actually very, very important. Magnetic field direction is this, okay? And xy plane is actually inclined to that, right? Xy plane is inclined to that because the particle motion has a pitch angle alpha. Okay, so this is the geometry. Okay, so let's see. Let's write n hat. So is this clear? This is a little subtle point. You have to think about this on your own again. So n hat is equal to cos theta x hat plus sine theta z hat, right? This is the direction. The n hat is in the xz plane, so this is very simple. Okay, so this is n hat. What about beta, the velocity? Beta is equal to, if you're at this position at time t prime, beta is nothing but beta times cos vt prime by a x hat, right? So this is the x component of the velocity plus sine vt prime by a y hat. The motion is in the xy plane. Okay, and this xy plane is along this pitch angle. It's sort of at an angle alpha to the magnetic field axis, and this is the angle z. This is the z axis, and this is the magnetic field direction. Okay, so this is beta. So we have to calculate n hat cross beta. So if you're given n hat beta, so the other thing is this is epsilon perp hat, right? We know that the radiation, right? So we know that electric field is always perpendicular to n hat, right? Because this is the electric field. It's always perpendicular to n hat, and even this guy is perpendicular to n hat. So we actually calculate another unit vector. So you have n hat, you have epsilon perp hat. We create another unit vector, epsilon parallel hat, such that epsilon parallel hat is equal to n hat cross epsilon perp hat, right? So so z xy, so n hat epsilon perp hat comma epsilon parallel hat is a triad, and these are unit vectors. And when you're looking at an angle n hat, your electric field will be polarized in the plane perpendicular to n hat. So it will have these two independent polarizations along epsilon perp hat and along epsilon parallel hat. Okay, so we can actually easily calculate epsilon parallel hat, which will be right. So we know n hat and we know. All right. So from this diagram, epsilon perp hat is nothing but y hat, right? I have chosen my y-axis such that the acceleration at t prime equal to 0 is along the y direction. So this is equal to cos theta z hat minus sine theta x hat. Right, so this is just the cross product of this and this. How do we? So xy is z, zy is minus x. So you get that, and that is also in the xz plane. So this is actually in the xz plane, and this is angle theta. So both n hat and epsilon parallel hat are in xz plane. So they are perpendicular to this y-axis. Okay, so let's calculate n hat cross n hat cross beta. This is what will be needed here, right? In this formula, we'll need this. So if we calculate that, we have n hat beta epsilon per parallel, all of those are there. We can actually write it in terms of, right? So since this is perpendicular to n hat, so we can write it as a linear combination of epsilon perp hat and epsilon parallel hat, right? Any vector which is in the plane perpendicular to n hat can be written as a linear combination of epsilon parallel hat and epsilon perp hat. And so that will also be true for this. So if you do the algebra, this is what you get. You get beta sine minus beta sine Vt prime by A epsilon perp hat plus beta cos Vt prime by A sine theta epsilon parallel hat. So these are the two polarizations of this quantity. So you'll have a component along epsilon perp and another component along n hat cross epsilon perp hat. Okay, so this is easy to see. You can actually show this. Okay. Okay, what else? We also need to calculate this exponential factor, right? So for that, we will need so r naught t prime, right? So this is the location of this charge as a function of time is equal to what is this given by, right? Actually, you can also see, like, this velocity is easy to see. At t equal to 0, this is along the x hat direction. And y component is of course 0. So similarly, r naught t prime, all you have to do is just, this is at time t prime. So this is its x coordinate, this is its y coordinate, and this is its x coordinate. So this x coordinate is nothing but a sine Vt prime by a. So let me just write down. So this is equal to a times 1 minus cos Vt prime by a y hat, right? This is nothing but this distance. A times 1 minus cos, so this is the distance cos Vt prime by a, and then this is this whole thing minus this is that plus sine Vt prime by a x hat. So this is your r naught. What do we need? We need this n hat dot r naught t prime. What is that? So n hat is this guy. So it only is along x hat and z hat. This is y hat and x hat. So this is simple. This is just A cos theta sine Vt prime by A. Right, so if theta equals pi by 2, for example, n hat dot r naught will be 0 because, n hat is perpendicular to the orbit. Okay, so how do I go down? I think I'll have to use this tool. Okay, good. Oh, shoot. This is really, really weird. It has this, it gets zoomed out a lot on a small touch of the mouse. Okay, I'll have to. Okay, I think this is fine. Let me not touch the mouse again. Okay, so so this is n hat dot r naught. So what do we need? We need t prime minus n hat dot r naught t prime by c. Right, in this exponential factor, we need this. So this is nothing but t prime minus a cos theta sine Vt prime by A. Now, what I'm arguing is that the radiation that you see at n hat will be concentrated at small theta, right? We know that that most of the radiation comes in a cone of theta of order 1 by gamma. So we can actually, we'll use this approximation, and Vt prime by A is much less than 1, right? Basically, only in this portion of this orbit, only for small angle theta and only for small angle Vt prime by A will you see significant radiation in this direction. Okay, so if we do that, what do we get? We get this is equal to t prime minus A 1 minus theta squared by 2. I'm just sort of expanding in small angle, and Vt prime by A minus 1/6 Vt prime by A cube. I've expanded this cos theta and sine Vt prime by A in small argument, and this is what I get. The other thing that I do is beta is equal to V by C. It's almost 1, so 1 minus beta is like 1 by 2 gamma squared. So this is what I'm going to use. So V is equal to C basically. Oh, okay, let me not do that yet, because there will be a cancellation. Because yes, so let's see. Let me actually just give one step and then write the final answer. So this is equal to, if I expand this out, this is equal to t prime minus beta t prime times 1 minus theta squared by 2 plus a by 6c 1 minus theta squared by 2 v cube t prime cube by a cube. So this is equal to, right, so this is This is T prime times 1 minus beta. That becomes T prime by 2 gamma squared plus. So I can put beta equals 1 at most places unless I have 1 minus beta. Theta squared T prime by 2 plus 1 by 6, 1 minus theta squared by 2 times C squared T prime cube by A squared. So, you know, I can ignore this term because anyway this is small. This is higher order. So what I have is iota omega T prime minus n hat dot R T prime or not T prime by C. This is equal to iota omega by gamma squared. So I can actually, you know, simplify this. 1 plus gamma squared theta squared T prime, right? This is just the sum of these two terms plus so iota omega by 2 gamma squared. I bring it out, so I have C squared gamma squared T prime cube by 3A squared. So I have this. This is that phase factor, right? That comes up in this formula for dw dt d omega, dw d small omega d capital omega, right? So this is the phase factor, and this oscillates wildly for gamma theta greater than 1 and right, so basically this becomes large, then it will oscillate fast, and even if this factor becomes large, so C squared gamma squared T squared by 3A squared greater than 1. So we can actually approximate this integral by assuming gamma theta to be small and approximate integral and C squared gamma squared T prime squared by 3A squared also less than equal to 1. Right, so this is just a, right, you know, I don't have to write these squares. So C gamma T by A is less than 1. And let's see, n hat cross beta has these two polarizations, right? This and this. So these are the two polarizations of the field. So we can actually write the expression for power for these two polarizations. So let's see, so n hat cross beta, this is approximately so again this can also be approximated a little bit. So let's see, how do we approximate this? This can be approximated because, right, we have, you know, again we have this Vt prime by A and theta. We can make the small angle approximation. So what do we have? We have, so this is equal to epsilon perp hat minus Vt prime by A plus epsilon parallel hat theta times 1 minus v prime t prime. I mean, this is anyway small. Theta is small, so we don't have to. We can actually neglect it. So we are only retaining the leading order expansion in the angles. Okay, so so this is this, and okay, let's see. So our total energy per unit frequency per unit solid angle is composed of two polarization. This along the epsilon parallel hat direction and along the epsilon perp hat direction. Okay, and if we plug these things in fact V is nothing but C, so we can actually just write it as C. If we plug these in, we get dW perp by d omega is equal to q squared omega squared, just substituting in that formula 4 pi squared C, and then you have this integral d. You have this integral Ct prime by a exponential of this phase factor, if you recall, which I expanded. Gamma theta gamma squared t prime plus c squared gamma squared t prime cube by 3a squared dt prime. So this is that expression, and these factors are nothing but this, right? This is nothing but that. And this is just n hat cross n hat. So this is this guy, right? So this appears as Ct prime by a. There's an absolute value square, and then there's this e to the power factor. Similarly, dw parallel d omega is equal to q squared omega squared by 4 pi squared c. Notice that there is a theta here, right? And this integral is over time, so theta can actually come out of that integral. So there's a theta squared because of the absolute value squared that comes out, and then you have integral of exponential of the same factor. Right, so this is the same exponential phase factor, because this part is the same for both polarizations, where gamma theta squared equals 1 plus gamma squared theta squared. Now we can actually simplify these integrals. We can simplify these integrals. We can have a change of variables again. We can have y is equal to gamma ct prime by a theta gamma. So basically this guy, wherever you have t, you can replace by y, and this is y, and you have another parameter introduced, which is omega a theta gamma cube by 3c gamma cube. So these are just to sort of make this integral more tractable. If we do that change of variable, we have dw d omega equals q squared omega squared 4 pi squared c. Actually, it's a good idea for you to work this out on your own. A gamma theta squared by gamma squared c. There's nothing really very tough, but it's a little tedious. And the other thing that you notice here is that, see here in this expression, we make the assumption that Ct prime by a is much less than 1, right? But here we actually take the integral from minus infinity to infinity, because we know that the integrand vanishes very, very quickly as you go to large times. For longer times, this phase factor oscillates very wildly. So there's a lot of cancellation. So it doesn't matter if this integral, the limits of this integral are changed from minus infinity to infinity, although we have assumed Ct prime by a to be small, because the contribution of the integrand beyond theta t prime, beyond theta of order gamma theta of order unity and c gamma t prime by a of order unity will be 0. So this is y exponential 3 by 2 iota. This is the mathematical version of what we already did. So I just wanted to do this maths a little bit because it's useful to know how these formulae come about. So this is this, and this is for perp, this is for, again, this can also be simplified in the same way. This is equal to q squared omega squared 4 pi squared c. Right, so there's a theta square here. So this is the big difference, right? There is no theta square. So this guy vanishes at theta equal to 0. So parallel polarization vanishes if n hat is along the direction of velocity. It's only the perpendicular polarization that you see. But at other, and whereas this guy, this is maximum at theta equal to 0. When theta is 0, at the angle theta is 0, this phase does not vary as fast. Right, so that's why you don't have cancellations. And this has this polarization has that interpretation that this is the electric field as a function of theta. This is your power as a function of theta, and it sort of peaks at an angle of order 1 by gamma. This integral falls off beyond an angle of 1 by gamma. Okay, so this is a gamma theta by gamma c squared. Right, so this does not have this y here, right? This prefactor, there is no t prime here. So this is related but not the same. So this is exponential. The phase factor is the same. This is the same. And these are standard integrals actually. You know the table of these integrals is available. So these are, let me actually write down. Right, so most of the radiation actually, which is dominated by this, comes close to theta equal to 0. Right, so your eta is approximately equal to eta evaluated at theta equal to 0. What is this eta? Eta is this. This is equal to eta evaluated at theta equal to 0 is omega a gamma theta. Theta gamma at theta equal to 0 is just 1, right? Because theta equal to 0, this goes away by 3c gamma cube, right? If you recall, this radius of curvature was related to, so if you recall, a was equal to v by omega b sine alpha, right? We can take b to be c. So this was a, and if you recall, there was another thing which was gamma c, this critical frequency. This was equal to 3 by 2 gamma cube omega b sine alpha. So you see, this actually can be written as omega by twice omega c, where these are, this a and the value of omega c have been used from here. So what it means is that these integrals right? So you're integrating over y. So this is all, these two things both are functions of eta, right? This guy will vanish for theta equal to 0 with this prefactor. So let's see. So what are these things? Yeah, it's a little tedious. What do I do? Let me actually just open the book, because I just don't want to write out things that are given in the book just like that. Where is the book? Just a sec. Okay, I'm there. So can you see the book that I'm sort of showing? Right. So this is what I had, and now you can actually write these in terms of these integrals. As I mentioned, that these are like standard integrals. So these are standard integrals. These are Bessel functions. These are modified Bessel functions of order 1/3 and 2/3. So these functions are known to us as a function of eta. And you can actually look at how the power in one polarization and the other polarization varies as a function of this angle theta. Now, this is fine. So this is for a particular angle. So this is right. So I told you that this eta is a function of this eta close to theta equal to 0 is a function of just omega by omega c. So this is only a function of omega by omega c. Right, and then there are these prefactors. Now this is as a function of frequency and the solid angle. We can actually, so these formulas can now be integrated over solid angle to give the energy. So this is only for a particular direction. Now you can integrate it over solid angle to give energy per unit frequency, right? And it's in the plane perpendicular to the this is in the plane perpendicular to the direction of acceleration, right? We assume that n hat was in the plane perpendicular to the acceleration direction. So this is sort of the geometry, right? So you have this helical trajectory of an electron. Okay, this is the direction of magnetic field. The velocity, right? Velocity is in this direction, right? We are assuming a constant pitch angle alpha here. So you have particles which are, gyrating with this pitch angle. So since radiation, most of the radiation comes in the direction of the velocity, this is the direction in which the radiation will peak, right? If you look in this direction, you don't see much. If you look in this direction, you don't see much. Only when you're looking at this direction of this pitch angle, when the velocity is directly pointed towards you, you see the strong electric field. Okay, so this electric field is confined to an angle theta which is of order 1 by gamma. So you see this geometry. This is the radiation pattern for a given value of alpha, and the whole annulus is filled because wherever you are, here looking here or wherever along that cone, wherever you are looking, you are basically seeing one particular phase in the orbit of the particle, right? If you're here, you're seeing the particle almost at the uh, when it is when it is sort of beaming towards you. When you're here, some other location of the particle will be directly beamed at that point. And some, at this point there will be some other position which is directly beaming this. So this is like axisymmetric in this angle. So at every, at any, in any direction along this angle alpha in this cone, you see equal and strong radiation. So what he's saying is that we can actually now integrate this radiation over solid angles. So how do you do that? This is the solid angle, right? So solid angle in this case is sine alpha d theta, sine alpha d theta, sine alpha d theta. D omega is just 2 pi sine alpha d theta. So what you do is you integrate these over 2 pi sine alpha d theta and integrate over all thetas. So you have the sine alpha factor, and you have these integrals. This geometry is very important to remember. The physical setup and the geometrical setup is extremely important. These formulae you can see in any book. They are not that important. Okay, and you can actually write these in sort of simpler forms like this. So these f and g functions are pretty widely used instead of these Bessel functions. Now you are sort of integrating these, right? So this is integrated over the solid angle. Again, this is the same thing actually. This is the same thing as before. But written in slightly different form. This is dw by d omega. Let's see. I wonder where this factor. So there's a gamma to the 4 here. There is okay. You substitute for a, right? We know that a. I was wondering where do all these things disappear. So this is a. A equals c by omega b sine alpha. So a is that. Let's see. So the infinite limits of the integral are convenient and permissible because the integrand is concentrated to small values of delta theta about alpha of order 1 by gamma. That is fine. Now, what has he done? The above integrals can be reduced further. So these are the integrals. I wonder how this. Okay. I think there is another. Okay. Right. So d theta, actually, right. So d theta will become d gamma theta, and so there'll be 1 by gamma. So I think somehow you do it. I'll actually have to figure this out. But you get these expressions. These are standard expressions that are used in the literature. That this is the energy per unit frequency integrated over all solid angles in the two polarizations. And again, these are the tables of these functions are available, f and g. Okay, so this was just energy per unit frequency, but we are interested in power, so you have to divide it by 1 by time period. right? And that 1 by time period is nothing but 2 pi by omega b. If you do that, you get this expression. And again, now this is the expression where omega does not appear anywhere except in x, and x was omega by omega c, right? Previously, when we did the qualitative treatment, we said that the frequency dependence of power is only in omega by omega c. So that you see there is no explicit dependence on frequency here. And this gamma also gets absorbed in that. So this is the these are the expressions that are used. 6.32a and 32b. Those are used most of the time in the application. So the sum of these two gives you the total power, and yeah, so this is how the power is distributed in the two polarizations. It's useful to know this asymptotic form of this function f, right? Because the total power is proportional to f, this function fx. So let me actually just draw this function fx for you. So in fact, it's actually drawn in the book. Let's see. Right, here is fx, and recall, right, so let me just try to draw it here too, fx, and recall that x equals omega by omega c, this critical frequency, which is proportional to gamma cube omega b sine alpha. So this is fx as a function of x. So at x equal to 0, which corresponds to 0 frequency, it has a cutoff. It has, how am I drawing it? So so it actually goes to 0. So rises, and then there is an exponential drop off, and it has a maximum at 0.29. This is fx. So the asymptotic forms are given here in the book. The asymptotic forms of fx are given here, so it's useful to remember that at small x, at small frequencies, this goes like x to the 1/3. It's pretty shallow. Okay, and there is an x to the half e to the minus x. So there's an exponential cutoff, exponential cutoff at frequencies greater than omega c, which is equal to gamma cube omega b sine alpha. So there is a characteristic frequency basically, right? And that's why you can actually say nu of the radiation that you observe is approximately gamma cube omega b, or nu b sine alpha. Okay. So this is one function. The other function is this g, right? So this g was f minus g gives you a sense of polarization in the other direction. So this I cannot change it. Right, so this is f function. This is f function. So g function is, looks somewhat like this. I actually looked at the literature. G function looks g also starts from 0, and it actually looks like, it peaks at a slightly higher value, and it sort of falls off in the same fashion exponentially, but it has a peak at about 0.4. So, so as you can actually see that this parallel polarization will actually be 0 at high frequencies, and now I guess this difference peaks where you have maximum, where this difference peaks, that's where you will have maximum power in the parallel polarization. Okay. Now this is power as a function of frequency. We can integrate over all frequencies to get the total power radiated, right? And these are the expressions. This is like a messy. There are a lot of special functions that are used. For example, so you have to do fx dx because you're integrating over all frequencies. So frequency has a one-to-one relationship with x. So if you do that integral, you may need these relations in terms of these gamma functions. In the end, the total power, which is nothing but this guy, P total as a function of frequency is equal to dp d omega d omega. So you have to do this, it's proportional to fx dx, right? And if you use these properties, this is the expression that you get. Now, if you assume a power law distribution of electrons, right? So this is the same calculation that we did in this order of magnitude way. Now, if we plug in the numbers, these magnitudes of different values at the beginning, this is the formula that you get, right? You understand what I'm talking about. I'm talking about this formula, right? So we derived or motivated at least the scalings of this formula, right, as a function of frequency and magnetic field and k. This is actually, if you put all these messy Bessel functions and f and g and all that, f functions specifically, you get this, right? And you can actually see the dependence is the same, right? There are these factors, of course, which depend on the power law spectrum, gamma to the minus p, and that p index. But you see that b dependence is, there is a b here and there is a b to the power of minus p minus 1 by 2. So this, let's see. I'm actually a little confused because here I have b to the power of p plus 1 by 2. This is b to the power of minus p. How do I get that? Maybe I made a mistake, but let's see. So the frequency dependence is, here is the frequency only appears here. So this is minus p minus 1 by 2. But it's saying that maybe, no, did I make a mistake here? Let me actually check. This is actually fairly simple. It should not be hard to figure out. So when you are doing like a quantitative modeling of some source and so on, you'll use this formula, right? You can actually apply it almost blindly. You don't even have to know where these things come from, but it's useful to know the origin of all these things. Let's see about this formula. So there is this b gamma to the minus p. Gamma is proportional to b to the minus a half. Oh, Just a second. Yeah, the book is fairly careful. There are not many typos or errors. So it must be something that I missed. So there is a B here. There is gamma to the minus P. Oh yeah. Omega C is EB by N, gamma MC gamma squared. So gamma is proportional to minus B to the minus a half, which is fine. And this is gamma to the minus P, so B to the minus P by 2. Oh yeah. So this is minus P by 2, right? No, but it's a IMAX. Yeah, gamma to the minus P, gamma. So this is minus half to the minus P. This becomes plus half, right? So this is actually wrong. Omega B, omega by B. So B plus P by 2. It's B to the plus P by 2. Actually, yeah, it makes sense that if you have higher magnetic field with everything else fixed, you should have more power. And then why is this not? Oh yeah, there is a minus there. So so P dependence is B to the plus P by 2, which is fine. But why is there a B to the plus half here? There is B to the 1. So minus, okay, yeah, this is correct. Sorry, my bad actually. Are people still there hanging out with me? So you see, this actually is plus 1 power and B to the minus 1. So minus 1 is plus. So this is minus 1/2. So 1 minus 1/2 is B to the plus 1/2 and B to the plus P. So which is correct actually. Okay, good. Yeah, sorry about today's class. The gadgets were not working for me today. Hopefully they'll be okay next time. Okay, so I'll stop the class. I'll stop recording and I'll stop sharing.